Okay, let's get right into it. What if I told you that you could build a powerful, lab-grade scientific instrument, something that usually costs thousands of dollars, for less than $100? Well, today we're diving into how the maker community, armed with just a Raspberry Pi and some really clever software, did exactly that. They've unlocked the science of spectroscopy for pretty much everyone.
And this right here, this really tells the whole story, doesn't it? On one side, you've got the professional gear, super powerful, super precise, but with a price tag that basically locks the door for students, hobbyists, you name it. And on the other side, the DIY Pi spectrometer. That cost difference isn't just a small discount, it's a revolution in accessibility. It turns a highly specialized tool into a weekend project for anyone with a curious mind.
So, what is this thing really? What does a spectrometer actually do that makes the professional ones cost so much money? Let's break down the science behind it. At its core, a spectrometer is an analyzer of light. You know how a prism splits white light into a beautiful rainbow? A spectrometer does that, but for any light source, breaking it down into its component colors or wavelengths. And here's the cool part. Every single element, every chemical, has a unique spectral fingerprint. By reading that fingerprint, scientists can figure out what something is made of, whether it's a star billions of miles away or a sample right there in the lab. The question is, how do you build something that can read those fingerprints without taking out a second mortgage?
Right? That complex analysis is why they're so pricey. But what if you could get shockingly good results using simple, off-the-shelf parts? Well, this is where the genius of the maker solution comes into play. The beauty of this whole design is just how simple it is. The Raspberry Pi, that's the brains of the operation. A standard Pi camera with an M12 mount, which is just a fancy way of saying a common screw-in lens you find on tons of little cameras, that's the eye. A cheapo CCTV zoom lens handles the focus. And for the prism, a pocket diffraction grating, something you can buy online for just a few bucks. Seriously, there's nothing exotic here at all.
And that was the whole point, straight from the creator, Les Wright. The goal was never to hunt down rare or tricky components. It was all about proving that a serious scientific instrument could be built by anybody, using parts that are super easy to find and even easier to put together. No fuss.
Okay, so this brilliantly simple hardware gets you in the game, but it's the software that takes his project from a cool science toy and turns it into a legitimate, powerful instrument. The first version was a great proof of concept, but a major software upgrade, well, that changed everything.
So the original software was pretty clever. It worked by looking at two known points of light, say from a couple of different lasers. And then it would just draw a straight line between them to guess where all the other colors should be. It was a good first attempt, for sure, but it had one big flaw. The physics of how light bends through a grating and hits a flat camera sensor, it isn't a perfect straight line. That simple line was just a rough approximation.
The real breakthrough came with Pi Spectrometer 2. Instead of that rigid straight line, the new software uses a bunch of data points to calculate a much smarter curve. This curve can actually bend and flex to perfectly match the real-world spectrum, which means it accounts for all those tiny little imperfections in the lens and the grating. Now, this amazing precision comes from a math trick called a third-order polynomial fit. I know, that sounds super intimidating, but stick with me. All it really means is that instead of using just two dots to make a line, the software uses 4 or more known points to draw a way more accurate curve. And more points means a way better map of the spectrum. That accuracy, that's the secret sauce.
So a fancy curve is the key. But how do you, sitting at home, create that curve without a whole lab full of expensive calibrated lasers? The answer is absolutely brilliant, and it's probably hanging right over your head as we speak.
The secret weapon is a totally normal fluorescent lamp. You see, those tubes have gases like mercury and other elements like europium, and they emit light at very specific, very well-known wavelengths. So you just point your little homemade spectrometer at the lamp, use the software to click on the different colored peaks you see, and tell it what they are. That's it. The software takes those known points and calculates that super accurate curve, perfectly calibrating the entire device. It's genius.
And the results of that simple calibration, a mind-blowing level of accuracy. This number here is the R-squared value. It's basically a score of how well the curve fits the real data. A score of 1 would be absolute perfection. Hitting a score with 6 nines, that's just phenomenal.
It's proof that this little DIY gadget can achieve a level of precision that seriously rivals instruments costing thousands and thousands of dollars more. So, we've got an incredibly accurate scientific tool, and we built it for less than the cost of a nice dinner out. Now for the really fun part. What can you actually do with it? This is where this whole idea of democratizing science gets so exciting. Let's check out the features that make this thing so powerful. The new software is just jam-packed with pro-level features. You can freeze the highest peak to capture something quick, like a camera flash. You've got measurement cursors to analyze any random point on the graph. You can export all your data for a school project or a research paper. The list goes on. But then there's the real star of the show, the waterfall display. The waterfall display adds a whole new dimension to your analysis: time. Basically, it takes a snapshot of the spectrum every fraction of a second and then stacks those snapshots, scrolling down the screen. This lets you see not just how bright a light is, but how its actual color changes and evolves over time. For watching anything dynamic, it is an absolute game changer. And when Les Wright, the creator himself, tested this feature on a tunable dye laser, that's a special laser where you can actually change its color, his reaction really said it all. Just pure awe at what was now possible with his creation. And this is that power in action. What you are looking at is the actual wavelength of a laser shifting in real time, captured perfectly. That smooth, beautiful arc of color changing from green to yellow to orange, that's a direct visualization of physics in motion. And it was all recorded by a homemade instrument. This isn't a toy anymore. It's a serious tool for scientific observation. Now, this project is incredible all on its own, but it's also part of a much, much larger and more important movement. So let's zoom out for a second and look at the bigger picture here. What makes this project truly revolutionary is that the whole thing, the code, the plans, everything is open source. That means it's completely free for anyone to use, to learn from, to tweak, and to make even better. It's not about one person building one cool device. It's about giving an entire global community the tools to build their own and then build upon that foundation, speeding up discovery for everybody. Which really brings us to this final powerful question. For centuries, the best tools of science have been locked away in ivory towers and expensive corporate labs. But projects like the Pi spectrometer are kicking those doors down. They're proving that with a bit of ingenuity and a spirit of sharing, breakthrough science can happen anywhere, in any classroom, in any garage, by anyone. So the question isn't just, what happens next? The real question is, what will you discover now that the lab is open to all?